While people are thinking, I'll start off with a question.
Okay, good luck.
We've seen a lot of heterogeneity of mineralogy going down. What do you guys really think the mantle looks like in the transition zone? Are we looking at the average mineralogy of the mantle, or are we looking at special zones that have been re-enriched and are very different?
I'll start with that. Yeah, I think...
It's an unanswerable question, that's why I thought it's good to start with.
So I think, well, my opinion is that there's definitely a sampling bias. I think any diamond sample is a biased sample because we select the sample and we don't analyze a full run of mine production, which is a biased sample in itself. But we do see overabundances in phases, so you can't directly map the percentage of... I mean, if you literally took the abundance of MgSiO3 and ferropericlase, then you'd conclude that the lower mantle would be a very ferropericlase-rich composition with a little bit of enstatite and not much else, and I think we'd all agree that that's unlikely. So there is a bias for various reasons. I think some phases just seem to be trapped more than others. I think some of these phases are forming and recrystallizing during the diamond-forming reaction as well, and so that also imposes its own bias.
We have, one thing that clearly I didn't mention before is that actually many ferropericlase in diamonds are really iron rich, so which is what we don't expect for the lower mantle. The lower mantle should have the typical magnesium 0.9, 0.85, something like that. In ferropericlase, in super deep diamonds, they even be iron dominant. So we are trying to submit a paper in which we think that the iron richest part of ferropericlase probably are not ferropericlase primary phases. And we think that only the very magnesium rich are the typical lower mantle ferropericlase, and probably there are some very good papers published just in 2018 that shows that the primary phase could be this Fe4O5, Fe5O6, and probably this material then exalts ferropericlase and magnesium ferrite, which are magnesium ferrite is another material that more or less is 6-7% of the ferropericlase in volume. In all ferropericlase rich in iron. So this is a very mystery.
Related to that, you showed in the sample you were showing where you did the X-ray tomography on the two ferropericlase inclusions, there were two other inclusions you didn't mention, a red and a yellow one, at least it appeared in the image.
Yeah.
What are those minerals, and do they better constrain where that diamond may have formed?
Well, one of that is mervinite.
Say that again?
Mervinite is a calcium magnesium silicate.
And does that give you a better constraint where that would have formed?
I mean, we have to understand mervinite can be stable in the upper mantle, okay? But if it's some transformation from some other phases, then it becomes more complicated to say. Yeah.
What about the yellow phase? Well, I don't know which one was the marinite, but the yellow phase?
Yellow phase. There was another phase.
It looked like there was a yellow and a red crystal in there.
No. If I don't remember, probably, maybe it's a surface material, could be. Sometimes you have this yellow, this orange for some alteration sometimes.
There is a lingering issue that's becoming increasingly more difficult to ignore. If we're talking about all these diamonds, some of which maybe are fist size, coming up from 600 kilometers, how are they coming up, and how is this related to kimberlites? Is any speculation?
Well, so I'll answer that from a geochemistry of kimberlites perspective, and you can solve the mineralogical problem if you want. Okay. One of my other interests is in the geochemistry of kimberlites, and archetypal kimberlites that these super deep diamonds come up in, they don't come up in lamproites, etc. There's a few sublithospheric samples in the Argyle lamproite, but they're pretty much exclusively in what we would call archetypal kimberlites, and those rocks, those magmas have the composition of the convecting mantle. And in fact, the recent heliumisotope study shows that they have the composition of the deep convecting mantle, Oib source rather than Morb source. So that gives you, so kimberlites are our deepest derived volcanic rock. My opinion is that their geochemistry is best explained by them being at least in the Oib source and deeper than that. So somewhere in the transition zone or even the base of the transition zone. So I think that they come up in kimberlites that originate at least as deep as that. Steve Haggerty's proposed depths much deeper than that, actually.
Much deeper.
There you go.
Can I? Okay, from a mineralogical point of view, there's a problem. There's a problem because everybody thinks, I don't know if everybody, many people think that if you still have ringwoodite preserved in diamond, this means that the diamond must be extremely fast in ascending. This is wrong. And I tell you why it's wrong. When the diamond enters in the elasticity regime, which we calculated is a 15.5 GPa, can be wrong, but not 10 by 10 GPa. Can be wrong, okay, 14, 16, we don't know exactly. But once the diamond enters in this elasticity regime, there's no way that you can transform any mineral in the lower pressure polymorph, because diamond would never allow 20-25% of volume transformation, which is required to transform, for example, perovskite in breite. Ross and Chiara calculated 28%. How can diamond can allow 28% of volume change in the elastic regime? This can be allowed only in the plastic regime, which is below 15.5 GPa. What this means? Probably diamond can just ascend at some velocity, can be a typical Welly mantle, I don't know, but can be slow, keeping the high pressure polymorph, because you cannot transform anymore that. And then in the craton, okay, then the story.
Yeah. So I think what it means is you can't really constrain it very well from a mineralogical perspective, because diamond's such a strong container, which is why I like to revert back to the kimberlite argument. And they are very special rocks. And I think it's no coincidence that you only find these really deep phases in kimberlites, not in lamproites, not in other magmas that sample the bottom of the subcontinental mantle lithosphere.
Could I ask just a quick understanding question? If there are no inclusions in the diamond, you cannot tell whether it's a super deep diamond or not.
That's not exactly true.
Is that correct or not?
The nitrogen content gives you a very important information. Many super deep diamonds have zero nitrogen or very low amount, 50, 60 ppm, against the lithospheric diamonds that have 1,000, 2,000 ppm.
But it's not,
you know better than me,
well,
sorry.
and you're right, that
that's
the majority of them are like that. The Karoe ones seemingly not so much, but so that's a good guide, but it's not an exclusive guide, and so you have to combine that information with the plastic deformation you see. A lot of these diamonds, apart from the ones Evan seems to look at, look absolutely, the ones that we can afford to buy look horrible. They look as though they've been to hell and back. They've got multiple growth centers, but critically, they also have incredible dislocation densities in them as well that seem to be very rare in lithospheric diamonds. So I think you've got to use a combination of things.
Yes.
So I have a question to both of you. And recent theories showed that there is a lot of ultra-high pressure minerals in the Tibetan ophiolites where they claim ultra-deep origin. And there is moissanite in there and there is diamond in there. What do you think about these ultra-deep origins?
Yeah, well, I think the recent papers that have come out showing alternative origins for those phases have to be taken very seriously, because my biggest problem with the people wanting these ultra deep phases to come up in the ophiolites is, if you look at the tectonic model, it's beyond imagination, the coincidence where they've got this huge piece of peridotite with seemingly ringwoodite pseudomorphs in it, being in place straight back up a subduction zone right into sheeted dikes and low pressure gabbros. That I find beyond comprehension. So I think those recent papers that offer alternative explanations for those phases, I'm putting my money on those, is the politest way I can think of putting that.
I agree.
So Ross, let's take the last question with Ross here.
Just a very brief question. You already mentioned that I'm as loud as mine. That these diamonds look horrible because the screen is clearly being dissolved and regrown. When you talk about the depth of origin of these these sorts of diamonds? Are you really talking about the majority of the growth being at one particular point, or is it possible that the diamonds are quite small, capture some lower mantle minerals, and then grow later on at some time during the ascent? Is there evidence from that in the mineralogy or anything else?
From my side, you're right. I only mean the time of entrapment of the inclusion.
But yes, but it's certainly the case that I'd view, I mean, if you look at my abstract, I'd call diamonds the mineral of choice in the mantle, and zircons are the mineral of choice in the crust. And zircons grow at multiple times, and diamonds certainly grow at multiple times. And many of these super deep stones have clear evidence of multiple growth centers. And I wouldn't be surprised if you could find a lower pressure inclusion phase in some of them as well. Yeah.
Thank you guys very much.